Hi everyone. Is this too loud? It's okay? Okay. Thank you all for coming. My name is Milky. I come from Infigo IS, Croatia, and my today's talk will be about defeating Windows memory forensics. Actually about reusing some well-known techniques, some well-known anti-forensic techniques and applying them to memory forensics. So here's the agenda for today, for tonight. First, I'll give some general overview of memory forensics. Why do we do it and how do we do it? I'll mention two processes related to memory forensics, namely memory acquisition and memory analysis. I'm sure that all of you are at least a bit aware of those terms and terms of computer forensics and anti-forensics techniques as well. So this part could be a bit boring to you. We'll then familiarize ourselves with the current state of the memory anti-forensic techniques, and then we'll take a deeper look into the memory acquisition process, and we want to see whether there are any issues, any weak links in this process. I will then present my own proof of concept tool that exploits these issues and which tries to hide arbitrary artifacts from the memory dump. And at the end of the presentation, we will try to come to some conclusions and try to find possible, some additional methods, some ways to handle these problems. A quick slide about me. As Carlos Garcia Prado in the next room would say, I'm nobody, but I'm currently working on a privilege escalation. By the way, I'm kind of sad that we are giving our talks at the same time because I think he has a very nice talk and I would definitely go listen to his talk, but unfortunately it's at the same time as mine. I'm also info security consultant. I'm the short one on the left. This huge guy on the right is Branko Spasojevic. Maybe some of you know him. He was here 2 years ago. He gave a talk on code deobfuscation by optimization. So cheers, Branko, if you're watching this. I'm also an avid cyclist. I like to ride my bike, especially over high mountain passes, but since it's hard to do so in this time of year, I rather hack or code. And this presentation is a direct result of this last bullet. Okay, so back to the topic. Why do we do memory forensics? Why anyone does it? Well, for more than a decade, prevalent method of performing forensics was doing disk forensics. But in the last couple of years, memory forensics is becoming increasingly popular. So why is that so? Because incident handlers figured out that there are lots of interesting information in volatile data. For example, some data can help incident handlers during malware analysis. Some malware can be obfuscated or encrypted while on disk and can be almost completely or partially in clean state in memory. Using memory forensics, incident handlers can analyze malware which is memory resident. Some malware is sophisticated and does not touch the disk, stays in memory, so it's not possible to detect them using disk forensics, but only via memory dumps. I mean, memory forensics is also interesting because it gives a snapshot of the current state of the machine that is being examined. You can look at the list of current processes, list of current threads, connections, and all sorts of things, but also the connections and processes that have been recently terminated. It's very interesting to incident handlers, but it's also interesting to the bad guys because, as we know, memory dump can contain some sensitive information such as passwords, for example, BIOS. You can even retrieve BitLocker passwords, TrueCrypt passwords, and passwords for all sorts of services and websites. How do we do memory forensics? Well, it has two consecutive processes. First process is the process of collecting the memory image or memory acquisition, while the second process is memory analysis or analyzing this image and trying to find some OS artifacts. Regarding the memory acquisition, from a software perspective, it can be done in two ways. First way is to use some third-party tool, and the second way is to use Windows integrated methods. When I say Windows integrated, one of the methods is to read the hibernation file. This file contains some data, forensically interesting data that will be used for booting the machine up from the hibernate state, and it can be forensically valuable. The other mechanism which is integrated into the Windows operating system, is the crash dump mechanism, which, if configured correctly, produces a memory dump. We'll see which memory dump, when the intentional blue screen of that is incurred. That definitely means that the machine will be rebooted, but the memory dump will be created. When we use external tools, most external tools produce so-called raw dump, which is an exact picture, an exact image of physical memory, while some of the tools also support proprietary Microsoft format, crash dumps, without causing the system reboot. There are many tools. Some of them are mentioned here, most notably Moonsol's Win32DD. There are many others, Memorize, FTK Imager, WinPMM, and many, many others. So how does acquisition actually work? Every memory acquisition tool has two components. First component is the user mode component. Second component is the kernel mode or the driver. Why does the memory acquisition tool need the driver? Well, after Windows 2003 Service Pack 1, it's no longer possible to map view of device physical memory from the user mode. So you need the driver to map this device, to access this device. Many memory acquisition tools are just using a driver just as a proxy for device physical memory, which is not a very good thing to do. We'll see why later. Some other tools are using documented kernel APIs, such as MMMap IOSpace, while others, most notably Win32DD, are using some undocumented kernel functions, such as MMMap memory dump MDL. This is the default setting of Win32DD. Regarding the format differences, crash dump, which is a proprietary Microsoft format, contains processor registers, but does not contain first memory page and memory reserved for devices. Raw dumps, on the other hand, do not contain processor registers, but they usually contain first memory page and device memory. I say usually because it's really a tool-dependent setting. Some tools omit the first page and device memory, so if that's important to you, if you're doing forensics, be sure to look at your tool documentation to see whether it omits the first page and device memory. Okay, so the next process is the analysis. Analysis is simply the process of reading the memory dump and trying to identify some OS artifacts from this dump. There are lots and lots of tools for memory analysis. My personal choice is volatility. You probably heard about volatility and used it. It's a very powerful tool. It has lots of plugins. It's constantly being developed. It has a very vibrant community, and it's a great tool. There are other tools, for example, Memorize or Mandiant Redline, which is a front end to Memorize. There are others, for example, HBGary Responder, Ncase has some plugins for memory analysis, and so on. Regarding the formats, all tools support raw dump format, so if you want to analyze your dump using multiple memory analysis tools, then be sure to use raw dump or to convert it from raw dump to other formats. The tools have currently weak support for crash dumps or other formats, so if you want portability, use raw dumps. Okay, so let's look at the big picture of memory forensics. How does the memory forensic work? Incident handler first starts the acquisition tool. This acquisition tool installs the driver inside the kernel. This driver uses some of the mentioned algorithms to map physical memory and reads page by page or some bigger chunks of memory and writes those chunks into the memory dump or sends this chunk over the network where the remote server is doing a write to this dump file. This concludes the acquisition phase of the memory forensics. Incident handler then launches analysis tool, which reads this memory dump and tries to identify certain artifacts from the memory dump. Okay, so let's see something about the currently known memory anti-forensic techniques. Let's start from the really simple ones and move to more advanced ones. First, really simple and stupid method is oriented towards acquisition blocking. So this method simply prevents memory acquisition tool from loading its driver or from starting. All those tools have drivers with predictable or well-known names, so if you disable driver loading with specific name, you effectively block the acquisition. There used to be a Metasploit script. If I remember correctly, it prevented Memorize from loading its driver, but it's not available anymore. I haven't found it anywhere. Anyway, this method is can be evaded really simple because you can simply rename the tool, effectively renaming its process, or you can rename the driver. That's easy if you have the source code. If you don't have the source code, it's nevertheless possible, but much harder. But using this method and blocking the complete acquisition, that rings all sorts of alarms for the incident handler, so he'll definitely, if he cannot proceed with the memory acquisition, he will definitely know that something is not right, and he will try to look deeper into the situation. So this is really not a cool memory analysis defeating technique. More advanced technique was proposed this year by Haruyama and Suzuki. Their work was called one-byte modification for breaking memory forensic analysis. What Haruyama and Suzuki did was they conducted the research on well-known memory analysis applications, and they figured out that all memory analysis applications have 3 key steps. They perform 3 key steps. First step is virtual address translation. Second step is OS and architecture detection. And third step is trying to identify some kernel objects, some kernel artifacts. And they did the research, and they found out that every tool has some so-called abort factors, that every tool has some issues with those 3 key steps. And for example, they found out that the HB-Gary responder is traversing the process list by first finding the PS initial system process or the process with the name system. So if you rename the system process to, I don't know, not system, the process traversing list will not work, and the HB-Gary responder will supposedly not be able to traverse this list. This technique is cool. It makes some subtle modifications. They can be really hard to detect. I mean, not this example with not system renaming, but some other modifications can be really subtle. The disadvantages of this technique are that it's not possible to hide absolutely any object inside the operating system, I mean arbitrary object, because that could cause some instabilities of the system and could crash the system. This technique also breaks the entire analysis or big part of analysis, and that can definitely raise some suspicion on the incident handler side. Another work on memory anti-forensics was proposed like 7 years ago by Sparks and Butler. Some of you might recall it. It's called, they created a proof of concept rootkit called Shadow Walker. What they did is they created a custom page fault handler, and they marked every memory location that they want to hide as not present, as being swapped out, as being paged out. Additionally, they cleared out the complete translation look-aside buffer and desynchronized the instruction and data translation look-aside buffer. By doing this, they actually made sure that every access to the memory location that's supposed to be hidden will cause a page fault, and their custom page fault handler will be called. In this custom page fault handler, they check whether the access to the memory location was read or write. If it was read or write, they simply disallow this access and redirect the caller to some arbitrary memory location. If this access was an execute access, they allow this access, so your rootkit is allowed to execute, but it's not allowed to be written to or to be read. This is a really cool technique and awesome idea because it's cool and because you can almost hide almost any object. But it certainly has some disadvantages. I tested it, and it's really unstable. It's completely unusable on multiprocessor systems because they didn't add MP support. I tried to add it, but it's simply not stable. Another thing is that the page fault handler itself is visible. So the code of the page fault handler is visible, and the interrupt descriptor table hook is also visible. You cannot hide it using this method. Another thing with this method is that it has some performance impact, especially if you try to hide multiple locations, because every access to the location will cause a page fault. Okay, so let's get back to this memory forensics workflow. Can anyone tell me what do you think is the weakest link on the memory acquisition side of the process? So concentrate on the memory acquisition.
Installing the driver.
Sorry?
Installing the driver?
Maybe, but you can only block the acquisition then. Exactly. Yes. That's the most critical part. The point where you are actually writing the dump or sending the dump over the network, sending the chunks of memory over the network, is the weakest link in the memory acquisition process. And if an attacker has kernel access, this is really a game over for memory forensics. I know that this sounds familiar because 6 years ago, Darren Bilby did a similar thing with the Defy rootkit. He created a disk filter driver which faked disk reads, and he faked mappings of physical memory, access to device physical memory. So I'm definitely not doing anything new here, but I'm just mapping, I'm just reusing old and well-known anti-forensic techniques and applying them to memory forensics. So you can think of this work as more as an evolution than a revolution. Okay, so it's time to introduce my tool. It's called Dementia, and apart from having a really lame name, it's a proof of concept tool for hiding almost arbitrary objects from the memory dump. It has user mode and kernel mode component, and it currently supports 3 methods of hiding. 2 are kernel mode related and 1 is user mode related. I'll talk about them later. It has been tested on Windows XP, on Windows Vista and Windows 7. It's more or less stable on all of those operating systems if there are 32 bits. On 64 bits, user mode injection is working, and the driver is very experimental, and I don't advise you that you use it. So how does Dementia work? As we saw previously, what we want to do is to intercept write calls, so to somehow control the process of writing the dump. There are 2 methods. Those are the 2 previously mentioned methods. The first method is to hook the anti-write file by placing an inline hook. I have tested it. It's not supported by Microsoft. It has been tested both on multiprocessor systems, both for hooking and unhooking, and it's pretty stable. But I don't know if any one of you is into driver development, but if you are, you probably know about Don Byrne. He's a guy from OSR online forum and mailing list, and if you ask him anything even remotely not supported by Microsoft, he'll freak out. And if you ask him anything about hooking, he'll probably kill you over the wire, so don't use hooking. The proposed method of intercepting the write calls, intercepting the process of writing the dump, is to make a file system mini-filter driver. So that's the second method Dementia uses. This is a really nice and really stable method, but from a Black Hat perspective it might be too noisy because it leaves a lot of artifacts inside the system, and you have to make sure that you clear all those artifacts, which can be daunting. Maybe IRP hooks would be a better solution, but I have chosen to write a file system mini-filter. As you also know, hooking is a big no-no in 64-bit kernels because of the patch guard, so you cannot just hook anywhere on anything inside the 64-bit kernels, so mini-filters are really the way to go. Okay, so now we have the hook in place, but what's next? How do we know whether the file being written is actually forensic memory dump or some other regular operating system file? Well, it turns out that all of the memory acquisition tools have some patterns. So when I say patterns, I mean specific anti-write file arguments. I mean that this calls anti-write file is executed from a specific context, from a specific process. We can detect the presence of a certain driver and so on. Also, a file object being written can have specific values and flags. This table below summarizes my research on those patterns, and you can read this pattern like this, this table like this. So, for example, FTK imager has anti-write file arguments such that handle is always in user mode, event, APC routine, APC context are always null, IO status block is in user mode, buffer is in user mode, length is always 8000 hexadecimal, and so on. And using this table, it's relatively easy to detect whether a file being written belongs to a memory dump, or represents a memory dump. What I also want to emphasize here are these two columns, handle and buffer. First column actually means whether the handle to the dump file has been opened in user mode or the kernel mode, and buffer, whether the buffer being written is from, originates from the user mode or kernel mode. We'll talk about them later, but these are very interesting. Okay, so now we have our hook installed, and we know that memory dump is being created, but what now? All memory acquisition tools work in a way that they read memory page by page or in some page multiples and write those pages back to the memory dump. One possible solution is to scan every buffer being written to the dump file and search it for some specific target objects, for some interesting object that we want to hide. Well, that method is okay. We can do that, but it's both slow, inefficient, and can make your life harder. We'll see why later. So my solution that I have chosen is that when I detect that the forensic dump is being created, that memory dump is being created, I create a sorted list of all physical addresses of my target objects and all objects that are related to my target objects. So, for example, when a buffer is being written, if that buffer contains any of the any physical addresses that I have collected, we simply hide them. We either delete them or change them. How do I know whether the buffer contains one of those addresses? Well, that's a simple part, because I know the current offset inside the file. So I know the current file pointer position. And because the file layout is equal to the physical memory layout, I know exactly whether the buffer contains a certain physical address or not. Okay, that sounds easy. But remember that we are dealing with undocumented kernel structures, that we are dealing with undocumented and unknown offset sizes, addresses, and everything else. Here we can see that eProcess block offsets differ from version to version of Windows operating system. It's of course different on 64-bit and 32-bit versions of Windows because of the pointer size differences, and we can simply, I could have hard-coded these offsets, but I wouldn't want to do that. So if WinDebug can do it, we can do it also. My idea was to use Microsoft PDB symbol files and use debug help API. This API is totally terrible. Don't use it if you don't need to. Avoid it at all costs, but okay, I did it and it works. So the mechanism works like this. The kernel, the driver, builds out the list of symbols that it needs. For example, process hider says, okay, I need offset of unique process ID, I need offset of active process links, I need this offset, I need that offset, I need the address of this function, and so on. And it sends this list back to the user mode. User mode contacts Microsoft symbol server and downloads the necessary PDB files, parses it, and fills out the necessary details and sends it back to the kernel. You might ask whether this is dangerous because we are sending some unknown and untested data from user mode back to the kernel mode, and yes, that's true. It's a valid concern, but I have not found a solution yet for this problem. I could have maybe contacted the server directly from the kernel mode and parsed the PDBs directly from the kernel mode, but that proved to be a bit too difficult, so I didn't do it. Okay, so now we have everything. We have our hook, we know that memory dump is being created, and we know all the offsets and all necessary details, and we can start hiding some stuff. Okay, regarding the process hiding, we first get our target process eProcess block and unlink the process from various process lists. For example, we unlink it from the active process list. By unlinking, I mean just rearranging the next and previous pointers. We also delete the process from the session process links. I will also delete it from the job list. It's not currently implemented yet, but it will be. It's not hard to implement it. We also delete the entire process allocation, so we delete the entire eProcess block. When I say delete, I don't mean we do anything on the live system. We are doing everything inside the buffer, inside the dump that is being written. So a live system is simply not touched at all. And then we hide related data. We hide threads, we hide handles, virtual address descriptors, and all other stuff. So it might seem that process hiding is really simple, but in fact it's not, because traces of process activities are literally everywhere. It's really difficult to hide entire process creation and open handles and all those stuff, and to remove it completely, I think it's very, very, very hard. We'll see how to delete some of the artifacts in the next slide. Also, as a note to volatility developers, it seems that just by deleting the process allocation, just by deleting the eProcess block, you are able to fool almost every volatility plugin that is related to process listing. Of course, you fool PSScan, but you fool even the PSX view. This is the plugin that was written for detecting such malicious modifications, so it should not be fooled by this so-called simple method. It seems that the main reason why is that so, why you can fool volatility, is that they use this dereference as call. It's trying to dereference unknown memory location as a known object, as for example eProcess block. But if this block does not exist, if process allocation has been deleted, this dereference call fails, and volatility simply ignores it and goes to other data, goes to other processes. So maybe a better solution would be to ignore checking the existence of eProcess block and its validity, and just leave the data and show it as is. For example, if we have a handle, and this handle is of type process, but it does not point to any valid eProcess block or process allocation, never mind, just show the handle. Just make sure that incident handler sees it, because it could mean some malicious, it could indicate some malicious modification. Regarding threads hiding, it's relatively easy. I mean, the methods implemented here are relatively easy. We delete the thread allocation, and we also remove the thread handle from the global list global handle table of thread and process handles called PSP CID table. Be aware that there are still some thread-related artifacts that are not hidden. For example, if thread has any locks, or if thread is a member of any wait list, block list, or something like that, it's not deleted from this list. And it could be possible to detect it, but every memory analysis application that I have tested completely fails to detect the deleted thread when you just delete the thread allocation, and that's even more so when you remove the thread handle from the PSP CID table. While the thread hiding was simple, hiding handles and objects is definitely not, and I think Dementia does a good job here. I first delete the process handle table. I completely remove the OBTB allocation, and I also unlink the table from the handle table list. I then traverse the process handle table and see whether there are any objects, any handles that are opened exclusively by target process. I do this by checking these by these two counts in object header. So if pointer counter and handle counter are equal to 1, this object is definitely opened exclusively by my process, so I can safely delete it. And I delete both the handle table entry and the object itself. If it's not opened exclusively by my process, by target process, I then decrement these counts, and I hide the handle table entry because it's safe to do so. Handle table entries are not related to the object itself, but they are related to my target process. Okay, but that's not all, because target process handle is also present in PSP CID table as a global handle table list, and it's also present in the handle table of CSRSS process. So I also have to remove it from there. I then find this target handle and remove it from these handle tables. As you can see, handle hiding can be really difficult. I'm sure that I have missed some parts of some artifacts that are not hidden yet, but could show some target process activities or traces. Another note to volatility developers: It seems that, as you can see in the picture below, it seems that they are traversing when listing active handles, they are traversing the list of active processes and then dereference the handle table list using the object table member of the eProcess block. And this is okay, but an attacker could simply unlink the handle table of his malicious process from the handle table list. That's possible to do. Your target process, your malicious process would not be able to open any objects or close them, at least using Windows mechanisms. You could write your own handle engine or something like that. But your process would still run, and the code would still work. So maybe a better solution for volatility is to write a plugin that does not traverse the handle table list, but scans for OBTB allocations instead, like they do for process allocation, thread allocations, and some other objects. For memory allocations, it turned out that it's rather easy, because all process memory allocations are described by virtual address descriptors. These are some simple kernel-level structures that describe memory ranges that are allocated by any process. These VADs are organized in a self-balancing binary tree called AVL tree, and the root of this tree is stored inside the eProcess block, and it's called VAD root. The hide algorithm is rather simple. I traverse the entire tree. I delete the allocation itself. I mean the VAD descriptor, not the allocation itself, but the VAD descriptor. And then I check if this VAD points to a private memory of the process. So if this is a memory that is allocated only by my process and it's used exclusively by my process. If it is, I delete the entire allocation. I hide the entire allocation. If this VAD represents my process memory image, so my exe, I delete that allocation also. If it describes some shared memory, for example, DLLs and some other files, I first check whether this shared memory is mapped only or used only by my target process. If it is, I delete it as well as the object itself. So the file object, for example, DLL, is also deleted. If it's not, I cannot do anything, so I just leave it be. I should have decremented the counters, but no memory analysis application checks for these counters, and it's really safe not to do so. But memory allocation hiding is relatively simple. Okay, so another thing that Dementia does apart from hiding processes is driver hiding. This support is rather weak and rudimentary, but it's effective nonetheless. I hide the drivers by unlinking the driver entry, the loader data table entry, from the PS loaded module list. I delete the MMLD allocation itself, so the loader data table entry itself, and I also delete the driver image in memory. As I said, this is very simple. It's not definitely a complete solution, because there are lots of other elements of drivers that need to be hidden also. For example, driver pool allocations, kernel pool allocations are not hidden, and this is actually a difficult thing to do. I don't know how can I do it, but we'll think about it further. We can also, I'm also not deleting symbolic links. I'm also not deleting driver objects, and drivers hidden in this way can be detected with volatility with, for example, Symlinks plugin and some other plugins. So the plugin that scans for driver objects and some other plugins. Okay, so it's time for the demo. Let's hope it works. Do you see it? Okay. Okay, so just a second. There are lots of open windows. Okay, so I'm going to start Dementia in kernel mode, this mode that places an inline hook on anti-write file. And I'm going to hide notepad.exe, and I'm going to hide the NTFS driver, which is present in Windows operating system. I couldn't think of a better driver to hide, so let it be NTFS. Okay. So here it writes some data. it successfully filled out the symbol list and found the notepad process. It's currently not doing anything. The hook is in place, but the forensic application has not, the memory acquisition tool has not yet been started, so it just waits for a memory acquisition tool. If we run a memory acquisition tool, I'll run, oh no, I won't run that. Oh, just a second. Where is it? Okay, here. I'll run Win32DD. I could run any memory acquisition tool, but Win32DD is really fast, so I'll use this one. I'll use standard values, so this method uses mmmap memory dump MDL method, so-called PFN mapping, and we'll create a raw dump file called test.raw. Okay. We can see here that the driver has detected some objects, some artifacts, and it's trying to hide them from the dump. Okay, so the process has finished. Let me unload the driver. So you see unhooking is working. And I'm going to list the processes using volatility, just a simple PS list. We should not see notepad.exe here. Notepad.exe has process ID of 3848. Okay, in the meantime, I'll also run Sessions plugin, which is a relatively new plugin for volatility. It shows the currently active Windows sessions. And this plugin is cool because many rootkits, although they do unlink the process from active process list, they are not thinking about session list. And although you cannot find the process in active process list, you can find it in the session list. And this is a true indication of a rootkit activity. So I'll run sessions also. If you move here, Notepad should not be here. I hope it's not. Can you see it? No? I could have grabbed it, but okay. Okay, it's not here. At least I don't see it. Okay, I'll also run PSX view to show that it's hidden from this plugin also. Let's get back to sessions. So also, notepad.exe should not be visible here. It should not be visible in any session, not in this session or this session with ID 1. Okay, I'm thinking it's not. Okay, cool. This count is also decremented, so if you count out these processes, this count should match. So by comparing the count, by counting out the processes and comparing it to the count above, it should raise no suspicion to the incident handler. Okay, let's get back to this plugin. Oh, this plugin is slow. Okay, let me run thread scan. Let's find threads related to the process with ID 3848. 3848. This plugin is slow. Maybe this one is faster. Okay. So when you see these entries false, true, false, 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 they are usually indicating some terminated processes or some minor issues with the PSX view plugin. I'm not sure which one, but as you can see, Notepad is not here, is not in the list of these processes, because the process allocation is hidden, so it shouldn't be present here. But it's also not in the list above. I hope it's not. If anyone can see it, shout. Okay, I think this works. Let me get back to... Okay, this one works also because no threads were found that are related to our target process, to our notepad.exe process, and the threads are removed completely. Okay, let's see about modules. Modules, let me find the DFS. Okay, I have like 20 minutes left. Okay, great. It seems to work. Let's get back to the presentation. Do you remember these columns? This was from the table that represented the patterns in memory acquisition tools. As I said, user mode handle means that the handle of the dump file has been opened in the user mode. Buffer user mode means that the buffer being written to the dump file is in user mode. Do you see anything suspicious here? Well, if memory dump is opened in user mode, then it's vulnerable to hooks placed completely in user mode. For example, write file hook or anti-write file hook. If the buffer is opened in user mode, and it's usually coupled with the file in user mode, with the handle in user mode, then the buffer was passed back to the user mode from the driver, and it's vulnerable to device I/O control or anti-device I/O control file hooks. If you look at the list of the forensic tools, of memory acquisition tools, all of them except Win32DD are vulnerable to user mode attacks. So the tools are simply doing it wrong. They are mapping the physical memory and they are returning the pages back to user mode, and the user mode itself is writing the dump file, which is a very bad thing. I have written a dimension model that can hide the processes, threads, and connections completely from the user mode. Unfortunately, it does require administrative privileges because the acquisition tool itself must run as admin, so this is a kind of disadvantage of this method. But to install the driver, you also need administrative privileges, so that's not a big disadvantage. It's relatively simple. It injects DLL to a forensic application process, to memory acquisition process, and currently only memorize is supported, but adding a new, injecting to a new process is really a simple thing to do. It hooks a device I/O control file using an import address table hooking, so it's really nothing sophisticated or something big. It does sound simpler than the kernel mode hiding, but it's in fact much more difficult. Why? Because you have no knowledge of virtual addresses inside the kernel. You cannot access kernel memory. You don't know what's inside the kernel memory, so you have no knowledge of kernel memory. Additionally, you cannot easily perform virtual to physical translation because all you get is physical offsets and physical layout, and inside this physical layout you get the virtual addresses that you don't know. So it's difficult to perform virtual to physical translation like volatility because you have partial knowledge. You have only the current dump, which is a page or multiple pages long. One solution, I mean, the tool works like this. I search the current buffer being written to memory dump, to a memory dump, and try to find some target objects. If I found the target object, for example, a process, I delete entire allocation. If I find some object related to my target object, for example, if I find a thread or a connection, I also delete it. So this is an easy part. Okay, but what about process list unlinking? Well, yeah, that's the difficult part. Why? Because when you have a process and you have pointer to the next process and pointer to the previous process, these pointers are virtual addresses, and virtual addresses inside the kernel. I don't know anything about these addresses, and I don't know anything about the objects, the previous and the next process. What I also don't know, and what's also possible, is that I encountered my target process here, so it's somewhere here in physical memory, and my previous and next process, or next or previous processes, have already been written to the memory dump, so they are at lower physical memory location, and that's a big problem. My solution is the following. So regarding the virtual addresses, to determine a virtual address of an object, I use self-referencing fields, self-referencing members inside the eProcess block. So for example, there are lots of lists inside the eProcess block that are rarely used. And if the list is empty, it's pointing back to itself. So by subtracting the offset of the list from the value, you actually get the virtual address of your eProcess block. I do it also for the threads, and I don't need to do it for the connections. I then cache this object inside the dictionary where my virtual address is a key to this dictionary, and I also remember the offset, the physical offset, where I encountered this object. And then I do the following. I fixed the dump. I fixed the previous and next pointers. If an object was in a lower physical memory address, I just move the file pointer of the dump file, do modifications there, change next and previous pointers, and restore the file pointer back to the current location. That's the solution to this problem, and it proved to be much more difficult than the kernel level modifications and hiding. Okay, so we can see another demo. It's not very interesting, but okay. So I have started the NC. It's listening on the port 12345, and I'm going to hide it using the user mode component. Just a second to get hold of this. Okay, so we are using the first method. We are trying to hide NC. Dementia is currently waiting for memorize to start. I'm going to start memorize. Memorize is really slow, so it will take some time, but okay. So it has detected memorize, and it has started to detect some objects inside the dump. Some of these objects are false positives, but nevertheless true objects are also detected, for example, Explorer, CMD, EXE, and other objects. In the meantime, let me prepare volatility. Just a second to see. Okay. It has not finished yet, but it will in a couple of seconds. It goes faster at the end because all of the data is at the end of the memory. Okay, cool. It's finished. Let's first list the processes, and let's do a net scan. Let's scan for network connections. Okay, so NC must not be listed here, and we should not see TCP port 12345 listening here. If that works, we are all good. Okay. We can just look at this this column over there or over there and try to see whether NC is listed here. Just a second. Okay, so it's not here. It's not here. And it's not here. Below our UDP port, so UDP connections, so it's oh, great. Okay, so the connection is successfully hidden. Oh, it does sometimes happen. Demo cannot go good, right? Okay, so sometimes the PS list, if the process is the last process in list, somehow Dementia does not perform unlinking well. And we can see that although NC process is not listed, PS list does list an orphan process, a process that is simply blank and has all fields set to 0. So that is definitely an indication for an incident handler that something might be wrong, either with the memory analysis tool or some malicious modifications have been made. Okay, nothing's perfect, but okay. Let's get back to the presentation. Okay, as you have seen, Dementia has limitations. I'll focus on the kernel level hiding. It's not currently hiding connections. It's not hiding registry keys and values. It's not you are not able to hide arbitrary files, arbitrary DLLs. Thread hiding can be improved. Driver hiding must definitely be improved. One functionality that Dementia currently lacks is self-hiding. Without it, it's useless in your rootkit arsenal. So it is possible to specify Dementia user mode process and kernel process, but it's not a real self-hiding. I also have to port it to 64-bit completely without crashes and other things. That's definitely a work in progress. Okay, so what we have learned is that the acquisition tools currently must utilize drivers correctly, because currently they are simply, most of them are returning buffer back to the memory and doing the writes from the memory to from the user mode to the kernel mode, which is a bad thing, as we have seen. And it's also slow, because the buffer is first returned to the user mode and then written to the dump file, which is slow and unnecessary. One good alternative is to use hardware acquisition tools, for example, FireWire memory acquisition. There have been lots of talks about FireWire, and it's cool, it works, it's great, but sometimes it's simply not possible, because your target machine does not have a FireWire port. It's even more so with the servers. So if you don't have the port, you cannot use it, and this can pose some difficulties. Another alternative is to use the native crash dump functionality, which is built into the Windows operating system. Why? Because this crash dump mechanism uses completely different functions from the regular operating system, and it's really difficult to subvert them. It's difficult to thwart this kind of mechanism, but it is possible. I have done some research on that. Another possibility is for an acquisition tool to perform anti-rootkit scanning. I think it's unnecessary and stupid, but that's also a valid alternative. And another thing, you can simply live with it, because hopefully I demonstrated that any kind of live forensics is inherently insecure, and always, if you don't have the control over your system, someone can have control over it, and someone can subvert it. Okay, that's it. Thank you very much. So the project is hosted here, but only a simple SVN structure is here. The code will be uploaded in the next few days when I chill out from everything. So.
Thank you for your talk. We have around 8 minutes left for a quick Q&A. If you have questions, please queue up at the microphones over there, here, and in the gangway there. We also have questions from the IRC audience, which we will start with.
So someone asked whether XORing the contents before writing out to disk is a measure to subvert your detection.
Sorry, I didn't hear it and I didn't understand it.
The question is XORing the contents before writing out to disk enough to subvert your detection?
To subvert my detection probably is, because NK-SWINN is doing some hashing before writing the contents down to the disk. It will subvert my tool, but it's not good protection, I think. I mean, if I can detect that the XOR is being used, or if I know the tool, I can simply implement that. Or I can. It depends whether it's storing the contents, the dump from the user mode or from the kernel mode. Because if it's storing the dump from the user mode, then I can hook device I/O control, and when the buffer is still not XORed, and I can modify it there. So it depends.
I am very sorry. I have to inform you that we have to cut Q&A short now. So if you have any questions, please do catch up with him after the talk.
Okay.